we can introduce our next speaker, Frank Fu. You ready? Fantastic. I can give you this mic.
Thank you.
Thank you.
Okay. How's everyone doing? Okay, all right, all right.
Can you do the timing?
Okay, spoiler alert.
Phone will die, so. Oh, Frank, I'll give you a 1 minute.
Okay, thanks.
Yeah,
thanks. Oh, so actually,
Frank.
we're co-presenting
Yeah.
myself and Edgar. So okay, I'll be quick. Do you start timing now? All right. So hi everyone. My name is Frank Fu. I'm doing my DPhil here, my PhD here in computer vision for robotics at the RI. I'm joined today by my friend and colleague Edgar from a postdoc from VGG, the Vision Group, and we'll be presenting 3D grounded world models. So we'll describe, very soon, like what that exactly means. But first, with a show of hands, like how many people have used an LLM today? All right, great. A VLM, like a vision language model. Okay, so great. Now, there's, so as you're aware, so like a VLM is basically your ChatGPT with, as it processes images. And that's become a very popular modality for AI models today in robotics. And I figured, in the context of lab automation, what's an example application use case? So this is not work from our lab or anything, but it's work that was presented last week at ICRA. That's like the biggest robotics conference. And it's from Siquan Hill et al. Showing, using the state-of-the-art vision foundation models to achieve to achieve the task of pipetting. And I'm showing this example to kind of describe, what's kind of the gap right now that we see for, from someone that works on computer vision for robotics, day to day. So in this context here, they're using a state-of-the-art, foundation model to perform the segmentation of the, of the pipette and other relevant elements of, of the task. And with the VLM, they're then able to generate a grasp pose, so basically just where the arm needs to be in order to achieve the task. And on top of that, so here in this fine motion of actually finally performing the pipetting, there's this visual feedback loop, where the model constantly detects where the pipette currently is versus where it needs to be, and that correction signal is what allows it to be able to accomplish this task, because obviously from the day-to-day, the exact locations of these pieces would move a bit, and the form of correcting that error is through this live feedback. Now, it sounds like everything's solved, right? Well, I guess obviously not. So there's still some limitations with just 2D visual foundation models. So the intelligence here is carried out, purely from the vision of these two cameras that I've highlighted on the left and right. And in going from that 2D view of the world to a 3D action that then the arm from a different perspective needs to achieve, there's still a bit of a gap. So we have semantic generalization, with these VLMs, they're able to understand and segment, internet scale of things that they'll encounter. There's even visual feedback from this detection, but there isn't a 3D grounding. And what that means is that actually in the setup of this environment, you'd have manual work of basically creating the correspondence between the 2D view and the 3D robot. So on the video here on the left, we're seeing the kind of the intrinsic calibration of the camera that's on the robot, and that's understanding how things project into the camera. And on the right, what we see is then this more tedious task of having to have a bespoke gripper that will then that's able to mount this calibration target, and then manually a user is then supposed to bring this target around the external camera in order to understand that mapping from the external camera to the robot arm. So that creates that correspondence. And of course, why is this all needed? So, to sum it up here in this diagram, so we have 2D perception from the camera here of where the different elements needs to move relative to each other, and that 2D information still needs to be transformed into this kinematic chain that of the robot arm that finally translates into the motion of the pipette. So, is there a way to, to bypass the need for all this manual work? And that's, what Edgar will be presenting, with the latest of, the greatest research in 3D grounded world models.
Yeah, hi everyone. So as Frank said, current foundation models are very good at language, but they lack a lot of the spatial capabilities that are needed for complex tasks. So I want to show a little bit of the research we've been doing and we think will eventually fit into these language models to allow more general robotics. So first work I want to show you is called NodeSlam, and it's some work I did during my PhD, and it's relatively old in the field of AI, but I think it has important components in the areas that are being currently developed in 3D understanding. So that's why I want to talk about it. And the main idea of this paper is we have images with partial observations of the world, and we're want to get a full reconstruction of the objects we're observing in order to do some robot planning. So this is a diagram. You don't need to look too much into it, but there's three main parts in this method. So the first is the image recognition, which is looking at the image and saying, okay, let's detect what kind of object are we seeing and segment out that object. So that's kind of the first stage of this pipeline. The second stage is a learning component of shape priors. So for this, we need a lot of data of shapes of objects of different categories we are interested in manipulating, and we kind of build a latent space that allows us to infer the full shape even when we have partial observations. And the third part is how do we put this together, and is through this render-based optimization. Yeah, I also want to show hands. Has anyone heard of NERF or Gaussian splatting in the audience? Yeah. So that's quite popular nowadays in 3D reconstruction, and it's basically answering this question of if we have an observation from images, how do we fit a 3D model to it? And it normally does rendering, so projecting the 3D shape into the image and using the error to optimize the shape representation. So this is some examples of this method. So first we just show like a depth camera observing some objects, and you see the measurement is quite noisy and partial. But then with these shape priors, we can obtain quite a full reconstructions of the objects we're observing. And particularly, yeah, this is the example. So this allows us to do, once we can fit the accurate shape models to the objects, in this case is mugs and plates, we can then do actually quite precise robot planning of manipulating the objects. So in this case, we're gonna use those shape priors to plan how to stack the different plates into a box and also place the mugs. So this is an example of using 3D models for robot planning where precise reconstruction is important, and where some of the purely image language-based models would actually, at the moment, struggle a lot to do this kind of very precise tasks. Okay. Yeah, so as I mentioned, those three elements in this system are currently actively researched on 3D computer vision. So image recognition, there's much better segmentation, classification, post-estimation neural networks. There's a lot of work on 3D shape priors, so there's huge data sets like object bears and models, for example, by Meta on using these data sets to fit general 3D models to objects and people. And as I said, the kind of render-based optimization is very popular, and there's even a recent release where Apple Maps is using Gaussian splatting to visualize city-scale maps. And the second work I want to show you is a recent paper on, okay, now we ask the question of, we want to reconstruct any video with motion and get the 3D geometry and tracking of the objects that we're seeing. And yeah, I want to mention this VGT paper, which was quite influential in computer vision, which is kind of changing the paradigm of doing 3D reconstruction, of saying instead of doing optimization, we just have a single transformer network, takes images as input, and maps it to a full 3D map. So it's much flexible and faster than optimization. And we did this, this work where we extended this method, but now not just reconstructing the geometry, but also reconstructing the motion of the objects in the scene. And yeah, these are some examples of the reconstructions, which just now need RGB monocular images, not any specialized 3D sensors. And yeah, we think this is quite exciting for robotics because it could allow learning from human demonstration video by being able to map, for example, egocentric videos of human performing tasks into the same space than the robot. So that would allow to more easily map what you're seeing a human do to what you want a robot to do. Yeah, so a bit of closing thoughts. We think frontier AI models possess a great deal of common sense knowledge, but mostly about language and images in a weaker sense. So they still lack strong spatial 3D understanding for performing more complex robotics tasks. And we think that in this, yeah, these two things will start joining, and we will get more powerful AI system with spatial understanding that can do useful robotics. And yeah, me and Frank had been kind of thinking, what will this unlock in lab automation, particularly in tasks where you have variability and it's not very, yeah, it's not very precise models that you have. So yeah, we're very happy to chat with anyone interested in this.
Thank you both. That was really great to see some of the detail behind it and some of the implications to the end. Yeah. So any questions from the audience for these two? Yes, one over here. I'll come to both of you. I think we have time for both. Thank you.
Hi. Thank you for a great talk. And I apologize if this is a bit of a naive question, but have you tried applying your tech to the really small scale, like you know, microscopy images, and trying to project 3D, you know, spatial behaviors at that level? Is it applicable at that level?
Yeah. So actually, that's the beauty of, like, I guess, pinhole projection. So even when, you know, in microscopy, you know, the scale of the actual dynamics are, you know, are very tiny, on the image, it's still actually a pretty large image, right? So, and the fundamentals of how these models work, you know, they're kind of invariant under, let's say, they're invariant in the sense that as long as there's resolution in the image to pick out the individual particles and track the objects, it will be able to generate the equivalent physics. So actually, a lot of times, the generated 3D model is metrically, let's say, known only up to scale. And that naturally, you know, allows it to scale down to the micro scale or even larger scales.
Very cool. We had another question here.
Yeah, thank you for the talk. It was interesting. I was kind of wondering about data. Like, I think it was on this second to last slide, you talked about using videos on the internet. And we know that with, you know, current LLM models, they're trained on like all the text on the internet, and that's part of why they can perform so well. And I guess for what you're working on, you'll need specifically videos that show, I guess, robots or like humans doing tasks that are relevant to what you want to perform with the robots. Is there kind of an issue in like the amount of data available? Do you have any thoughts on like if more is needed and how the amount that's available, what kind of performance you'll be able to get from what is available?
No, definitely. I think in robotics now one of the biggest questions is how to obtain data, and people are figuring it out. There's different kind of data, and the method we showed on getting 3D from humans is one direction that people might think might be more easily to collect data for teaching robots, because you could just show examples of human doing stuff. So that's why there's a lot of promise in this method. But a lot of people are collecting data for robotics with teleoperations or remote controlling of the robot. So I think robotics now is kind of in that quest to collect a lot of data, but exactly what kind of data is still a very open question. Yeah.
Thanks.
Yeah, there's one more.
Thank you. It's a really interesting talk. So I'm quite interested in like around the 3D grounding. So I'm sort of wondering like about the angling of the two cameras. Did anyone try, for example, like angle like our eyes that's just looking at the same frame but just angled differently, so they can just calculate the difference by the depth, sort of like by that to infer the depth. Did someone try something like this before?
Yeah, absolutely. So actually the visual stereo that we have, it's not new in robotics, but it's, I guess, the grounding, so being able to pick out depth is one element of it, but actually with what we mean by 3D grounded world models is that actually there's a sense of also how the 3D evolves over time, and that's not something that we could resolve with just having stereo disparity to create depth. So that there's, and I guess we haven't presented here. The goal is to like eventually then have a predictive nature to it as well. So then from a few frames you're able to better predict how the 3D will unroll. So encoding the 3D dynamics.
Amazing. I think can we give another round of applause and thanks again. Thank you both. And so we have our last